Okay, so here's a graph. Here's a local maximum. Look what's happening with the derivatives to the left of the local maximum. They're positive. Until we hit the local maximum, we have positive derivatives. And to the right of the local maximum, we have negative derivatives. So if you have slopes that are positive right up until you reach the critical point, and then they're negative, then you've reached a local maximum. And the opposite's true here. If you have a negative slope, and then you hit the critical point, and then a positive slope, if it goes from negative to positive, then you've reached the end of the valley. Then you have a local minimum. You know, if you're going up on a mountain, you're climbing up, you're gaining elevation, and then all of a sudden you start losing elevation, then clearly you hit the peak back there. Okay, so with this problem, they've kind of taken care of all the first derivative stuff for us. They already analyzed the derivative. We're really interested in places where the derivative switches, signs. Okay, so here on the interval -2 to 2, we have a negative sign for the derivative. That means the graph is decreasing. But then from 2 to 3, the graph suddenly changes and starts increasing. So here at x equals 2, the graph switched from going decreasing in slopes to increasing. So that is a local minimum. This question is asking for x for local maxima, though. So local maximum, we said to have a negative derivative. Local maximum is positive derivative, switches to negative derivative. So positive derivative switches to negative derivative. So at x equals 3, we were positive a little bit to the left, and then we were negative a little bit to the right. So that must mean we hit our maximum there. So in order to use the first derivative test, we should probably know what the first derivative is. So differentiating this function means we're going to need the product rule because it's two distinct functions of x being multiplied. So the derivative of the first function, using the power rule, and we also need to use the chain rule because there's a value for the derivative of the innermost function that would change things. Derivative of 2x minus 2 is 2. So this is the derivative of the first function, and this is the second function kept the same, plus the first function unchanged, times the derivative, oops, I didn't do the derivative, times 2, the derivative of the second function. There we go. So when we want to try to find local max, local min, we find critical points, and then we test those critical points. Critical points occur where the derivative equals 0. So I want to set this derivative equal to 0. So 3 times 2 makes 6. And then this big term over here also has a coefficient of 6. Okay, and then look at the two terms and see what we can factor out. Because if we factor this, it'll be easy to set it equal to 0. So both terms have a 6 that we can factor out. Both terms have at least 2x minus 2 squared. And both terms have a 3x minus 1 to the first power. So left over, when you divide this term by 2x minus 2 squared, by what we found in common was we were left with 3x minus 1. And then here, if you factor out the 6, you factor out 2 of the 2x minus 2 squareds, so we're left with 2x minus 2 over here, because the 3x minus 1 also got factored out. And then if we simplify a bit, (3x minus 1 plus 2x), so 3x plus 2x makes 5x. (-1 plus (-2), that makes (-3). And now it's all factored. So if you set each factored piece equal to 0, this one's going to give us x equals 1. So I'll put x equals 1 right here. If you set this equal to 0 and solve, oops, here, that's 1. I'm going to put 1/3 here because it's a number line. No, because the next one's also going to be a fraction. So let's put x equals 1 over here. So this one, if you set it equal to 0, then x equals 1 would make this whole right side equal 0. Here, if you set x equal to 1/3, then this whole thing becomes 0. And then here, if you set x equal to 3/5, that makes the whole thing equal 0. Okay, so we found the 3 critical points, and what you'll want to do is test values in between for the derivative. So I'm going to test x equals 0, because that's something to the left of this one. Trying to think of something easy. So actually 1/2 would be an easy one to test between 1/3 and 3/5. That's the easiest I can think of, at least. How about 4/5 between these 2 critical points? And then let's plug in 2 for a value to the right of this one. You can plug in whatever number you want as long as it's between the other critical points, because we're looking to see what happens to the sign of the derivative. So we actually don't care exactly what this number is, we care about what sign it creates. Okay, so if you plug in 0, this term is always going to be positive because it's being squared. So we'll just forget about this. We'll just remember that that's positive. If you plug in 0 here, you get a negative term, so positive times a negative makes a negative so far. And then if you plug in 0 here, you get a negative, so negative times a negative makes a positive. So this has a positive derivative at x equals 0. If you plug in 1/2, then it doesn't matter, this term's always positive. 3/2 minus 1 is a positive number, that's 1/2. So far, positive times a positive makes a positive. If you plug 1/2 in here, 5/2, which means 2.5 minus 3, that gives us negative. So positive times a negative means this derivative is negative. Do the same thing with 4/5. This term is always positive because it's squared. 3 times 4/5 makes 12/5. 12/5 minus 1, that's positive. So this is going to be 4 minus 3, so this is going to be a positive. And then here, if you plug in 2 into the derivative, this is always positive, this is going to be positive, and this is going to be positive. So we didn't alternate signs in this last one. Okay, so using the first derivative test, we went from a positive slopes to negative slopes at x equals 1/3. So that's a maximum. Right, because at x equals 1/3, we hit a peak. The slopes were positive to the left of it, and then the slopes became negative to the right of it. So x equals 1/3 is a max. It went from negative to positive, so that means this is a minimum. X equals 3/5 is a minimum. And then we didn't change signs here, so this is neither a max nor a min. Okay, so this one was a maximum, this one was a minimum.